Assalamualaikum and a very good day to Dr. Fatimah and friends. We are from Group 5 and today we will be presenting about Bioimpedance Boca. These are our team members which consist of me, Nurul, Nadia, binti Mohamad, Zaini, and other 3 members which are Yan Yee, Syafika, Amalin, and Turukesh. This is the overview of our presentation. Shown here are the objectives of our group. Bioelectrical impedance analysis functions for analyzing body composition including fat percentage and body water content. It is quick, simple, non-invasive, mobile and functions independently. BIA is safer than DEXA because of its lower radiation risk, more precise than caliper test, and requires less patient preparation than densitometry. Impedance is measured at a single frequency or throughout a spectrum, which varies depending on the volume in the area. Some factors that can affect BIA readings are electrode arrangement and polarization. BIA has been applied to various techniques for diagnosis, including ICG for cardiac output estimation, EIT for image purposes, EIS, and IPG. It is also used for disease detection such as heart failure by identifying fluid shift through a rise in impedance in accumulated fluid locations due to higher extracellular water content. BIA can also detect liver disease such as ascites because of the increased abdominal impedance. Changes in total body water from intracellular to extracellular regions can be seen by BIA, which may indicate the start of ascites. Kidney disease can also be identified by BIA. Impedance increases in edematous areas is a way that BIA can detect fluid changes. This is the block diagram of the BIA system. The first block is the power supply with components such as switches, batteries, and voltage dividers which function to provide voltage for the analog and digital block. In the analog subsystem, the components involved are sine wave generator, AC to DC converter, instrumentation amplifiers, bandpass filters, and VCCS. It is used to deliver currents into the body to measure the voltage that will be used to determine the body impedance. Components involved in the digital subsystem are 80MEGA32 microcontroller, 4x4 keypad, and LCD. In this block, the impedance and body fat percentage are also computed. Based on the shown figure, current can flow to two sides of the body indicated by red arrow and green arrow. Current entering the body through various pairings of nodes travels through distinct pathways and finally produces varying impedances. The current electrodes receive input stimuli from a current source and the voltage electrodes detect the output signal. The detected signal is then collected up and sent via a signal processing system to acquire the necessary signal component. Driving circuits with regulated current magnitude limits below 0.25 mA supply the input current to ensure no shock to patient. To compute the impedance effect in the cells, the alternating current with a frequency of 50 kHz was provided.
Now, moving on to the theoretical calculation of leakage current. The circuit on the right-hand side is designed by our group based on the standard body model which is on the left-hand side. There are slight changes made due to the electronic components constraint from the medical electronic lab. The total capacitance of 0.015 microfarad is achieved by connecting one 0.01 microfarad capacitor in parallel to two 0.01 microfarad capacitors that are connected in series. The value of resistance and capacitance measured with multimeter is highlighted in yellow color in this slide. First, we need to calculate the total capacitance by resolving the capacitors of C1 and C2 into C12. Then the C total can be obtained by adding the C12 with C3. The final value is 14.42 nanofarad. Next, we calculate the capacitive reactance by using the formula of 1 over 2 pi Fc, where F is the frequency and C is the total capacitance. In the third step, the measuring device total impedance calculated is 962 ohm. Lastly, the leakage current is calculated by using the Ohm's law, V equals to IR, where V is the AC voltage across capacitor, I is leakage current, and R is replaced with the total impedance.
Hi, I'm Syafika and I will explain about the test procedure of this bioimpedance data. For the first one, we will test the Boca using the bender unit with applied part, without applied part, and also single test. And the second one, we will test using Rigel self-test 90 for the earth leakage and enclosure leakage current. And for the last one, we will test this Boca using our own measuring device. Firstly, we will use the bender without any applied part for our testing device. So this is what we will be shown on the bender's monitor. For the first one, we choose F3, which is the classification. And moving on to the standard, we choose F1, which is the IEC 601. And then we choose the protection class 1 for this Boca device. After that, we will choose the standard device, which is the general one, and type BF for this Boca. And then this is the crucial part to differentiate between the without applied part and also with applied part, which is the patient circuit lead. We choose the F1, which is the without applied part. And then we complete the test and we choose the F1, which is the automatic test sequence. The Boca undergoes testing in both normal and single fault condition, and the recorded value for protective earth continuity and earth leakage current display on bender's monitor. Secondly, benders with applied part. For this one, we will use the same steps as bender without applied part, except for a slightly different step, which is the first one is the number of patient circuit lead. We will choose F1, which is the with applied part, and we will choose number of leads of 6. And then we will press F3, which is the test without main voltage on applied part, and we will choose patient leakage current measurement with AC and DC part and proceed to direct. For the third one is single test. For this single test, the step R, for the first one, the Boca X1 was connected to bender safety analyzer, and then bender was linked to the power source, and we will switch on the power source. And then we will choose F4 single test. in the main menu, followed by enclosure, leakage, and patient auxiliary current for normal condition and also single fault condition. After selecting the preferred leakage current option, bender's test probe will then connected to Boca S1. And then we need to press the enter key to start the chosen. Next, moving on to the second testing device, which is the Regel self-test system. This Regel system can test the earth leakage current and also the enclosure leakage current. So the step for these two is almost the same except for the step 5, which is the buttons shown was pressed to test the earth leakage current, and this button was pressed to test the enclosure leakage. Next, our own design measuring device. A circuit was constructed to access various types of leakage current in a Boca under normal condition. This include earth leakage current, enclosure leakage current, patient leakage current, and also patient auxiliary current. The self-developed prototype of the measuring device is shown in figure here. The test current comprised of two 0.01 microfarad capacitor arranged in both in series and parallel with another 0.01 microfarad capacitor, as well as a 1 kilo ohm resistor and 10 kilo ohm resistor connected in series. One connection is linked to the Boca, another to the transformer's earth pin, and the remaining two connections to the multimeter. First, earth leakage current test. From the circuit diagram above, the earth connection of the measuring device is linked to the earth pin of Boca device, which correspond to the grounds of the Boca's power cord. Then, another earth connection from the measuring device is established with the earth pin of the transformer. The live and neutral pin of the transformer are aligned in accordance with the Boca pin. The remaining two connections from the measuring device are attached to the multimeter. For the enclosure leakage current test, all the connections are the same with the earth leakage current previous, but then there's a few exceptions, which is the earth connection of the measuring device is linked to any exposed metal part of the cases of Boca device. For the patient leakage current, the connections are the same except for the earth connection of the measuring device is linked to one of the applied part of the Boca device. And for the patient auxiliary current, the difference between all these current tests is that for this test, both connections of the measuring device are linked to the applied part of the Boca device.
Now let's take a look at the discussion. The electrical safety test is conducted on the assigned medical device, which is bioimpedance Boca using bender, Rigel, and the self-designed measuring device in 4 different modes. Bioimpedance Boca is analyzed under normal condition and single fault condition. The single fault condition for earth leakage current is open neutral, while the single fault condition for enclosure leakage current, patient leakage current, and patient auxiliary current are open. Besides, for electrical safety using bender, 4 different modes of testings are used, which are automatic, semi-automatic, manual, and single test. From table 1 of the result, we note that every value of leakage currents are measured using bender in 3 different modes without applied parts. We observe that the earth leakage current for both normal condition and single fault condition are below the IEC 60601-1 test limit. From table 2, we know that the enclosure leakage current and patient auxiliary current can only be measured in single test mode, while earth leakage current and patient leakage current can be measured in automatic, semi-automatic, and manual mode. The values for leakage current is all below the IEC 60601-1 test leakage current and enclosure leakage current measured using the Rigel Safe Test 60 according to the IEC 60601-1 test. From table 4 of results shows the measurement achieved by using a self-designed measuring device. Every leakage current measured using the self-designed measuring device is measured under normal conditions only. There is no test for earth leakage current under this condition because there is no limit according to the standard. The 3 other leakage currents, which are enclosure leakage current, patient leakage current, and patient auxiliary leakage current, are all measured 0.1, 0.01, and 0.01 respectively, and below the test limit according to the IEC 60601-1 standard. Hence, the bioimpedance Boca passed the electrical safety test and it is safe to be used. The percentage difference calculated for both leakage currents measured are high and indicate low reliability shown by the self-designed measuring device in performing electrical safety tests compared to the bender and Rigel 60. This proves both bender and Rigel 60 have better and higher sensitivity compared to the self-designed measuring device. Discussion on limitation, improvement, and precaution. One of the limitations we observed during designing the self-designed measuring device is to find the exact value of the capacitor of 0.015 microfarad, which is the standard value from the IEC standard. This is because we are unable to obtain the exact same capacitor value from the medical electronics lab due to component constraints. We achieved 0.015 microfarad, two 0.01 microfarad capacitors connected in series, and another 0.01 microfarad capacitor was connected in parallel. The need to use 3 capacitors and other electronic components may produce more noise. To overcome this limitation, it is advisable to purchase the exact value of capacitor for the self-designed measuring device. As a result, less noise will be produced and accurate readings of measurements be obtained. Moreover, there are more improvements that can be made on the self-designed prototype. The resistor and capacitor values utilized in the developed measuring circuit should be as near to the values suggested by IEC body model. This will improve the accuracy of the findings when the electrical safety test is carried out. In addition, the jumper wires connecting the multimeter, transformer, and medical equipment should be in different colors to avoid confusion. When doing the electrical safety test, there are certain precautions that need to be followed, such as wearing rubber gloves, turning off the transformer power supply, and avoiding handling the equipment after the test. Table 1 shows risk evaluation and risk control, where 3 processes are turned from as low as reasonably possible to acceptable, no further action required after the risk being evaluated and controlled. Table 2 and 3 shows the risk acceptability metrics before and after the risk evaluation and control respectively.
In conclusion, the electrical safety tests are crucial to evaluate the device performance and identify the potential risk of electrical shock hazards to user. Bioimpedance Boca passed the electrical safety test and is safe to be used.